Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. In fact, today is the last synchronous edition that we'll have. So the last lecture I'll do asynchronously because we're using the last lecture for the test. And we also have a quiz coming up that I wanted to squeeze in just before the test. So normally I wanted to put the test on that Sunday and we'd have our last class on Monday, but I thought maybe it would be nice to give you a test to finish up what we talked about derivatives to get some practice on that. And then you have the test on Monday. So I'll be posting that video asynchronously. What else do I want to say? I think that's it. As for the quizzes, I think someone told me that quiz 4, the grades weren't up. So the quiz is auto graded, but I manually go in and I have to click to make sure you guys can see it. And I guess I didn't do that, as well as I need to transfer the grades to Jupyter so that you see how it actually affects your grade, because it affects it differently when I put it into Jupyter, because there's a curve and there's a different total and all that stuff. So that hasn't been done yet. I will do that I'll do that right after class, in fact. So you'll see what was going on in quiz 4, might help you out with the test. And on the class webpage, of course, there are old tests that you can start practicing. And you may as well also start practicing old finals, I guess. But you can put that off for a little bit. You can put that off until Monday, I think, after your test. I think that's all I want to say right now. Let's actually jump into it. We're in the last sections. So we have about 2 more installments. And we're just starting. Okay, there we go. We're just starting the second part of the course, which I know seems like a little bit late, but it's actually not. Usually how it goes is that in a Calc 1 class, we kind of introduce you to the idea of what I'm going to talk about, the idea of integrals. And Calculus 2 is what goes into the study of integration and its applications and blah, blah, blah. But we just sort of give you a little primer, introduce you to a little stuff, have you be able to do some basic computations with it, know what it is, what it's about, what they are about. And yeah, you can go off into Calc 2 like that. Now, of course, most of you would never have to do Calc 2, so you don't really have to worry about it anyway. But that I just want you to know that it's normal to start the second part this late. It's not like, oh, we have half of calculus is about this and the other half is about that, and then we started half like with 2 sessions to go. It might seem weird, but that's normal. So we are going to do 3 or 4 sections. So 5.1, 5.2, 5.3. 5.1 we're going to do right now. 5.2 I'll start, and 5.23, or I think we skipped 5.3. We're doing like 5.4 or something. But there are like 3 or 4 sections, and I'll finish that up in the last session asynchronously. Yeah, so let's actually get into it. We are, as you can see here, attacking the area problem finally. So going way back, way back, in the very beginning of the course, I told you that, oh, what is calculus? And we spoke about it. Oh, calculus is the study of these 2 things. What is the point of these 2 things? And I mentioned that calculus is about, as we know it today, it's really the study of solving 2 special types of problems and all the collateral benefit we get from being able to solve these problems, because we solve the rate problem with the derivative and we realize that the derivative is actually way more useful than just figuring this one thing out. Figuring out how fast something moves, we can also figure out maximums and minimums. We can optimize situations. We can figure out related rates. We can do a whole bunch of stuff just by figuring out that problem. Integration is very similar, and integrals are very similar. So yeah, I'm just going to introduce you to the object and not so much all the ways we can use it, but it's also just as useful. So the two problems that we wanted to attack were the rate problem and the area problem. So the rate problem is figuring out how fast something is moving or what's the rate of change of something, whereas the area problem is about how much space does something take up, right? Now, normally, this question is not that bad to us at this point in our lives in math class because, you know, we learned about geometry. I know how much space a rectangle takes up. I know how much space a box takes up. I know how much space a sphere takes up. The problem is when you don't have these nice regular shapes, the problem is a lot different. So for example, if I give you this random blob and I ask you, what is the area of this blob? Right? It's a very different question, right? You don't have a nice formula for it. And even if you could come up with a nice formula for this blob, I could just draw some other random blob. Okay, what's the area of that? And now you'd have to come up with a whole new formula. There's no right, there's no nice systematic way to come up with a formula for every random blob that someone could come up with. So the area problem is seeking a solution to that. Is there a sophisticated way that we can go about solving, finding the area of some random thing or the volume of some random thing? And yeah, you might want to think, why is that important? It is very important for many reasons. One example is, let's say you own a plot of land, you're a farmer, way back in the day, you know, the taxman comes and say, oh, the king wants to charge you property taxes for owning this much land. And he's gonna like, well, this is how much you owe. And like, well, that's based on how much land I have. How do you know how much land I have? Look at my land. It's like, it's a weird shape. It's not a rectangle. It's not a circle. It's not that, you know, it goes around this tree and it goes through by my neighbor's thing and it cuts back around the river. Like, how do you know how much land I actually own, right? So how do you know that the taxman is charging you appropriately? You're not overpaying your taxes, or more importantly, you're not. You don't know to stay quiet if you're underpaying taxes. I'm kidding. Don't evade taxes. But that's an idea. Sometimes knowing how much space something takes up is very important. A lot of times you're renting stuff. It depends on how much space you're getting. So just knowing how much space something takes up is very important for a multitude of reasons, but that's just one of them. So let's just assume that this question is important because it is, and just move on to how do we actually solve it? Well, it turns out the solution to the problem is pretty basic in the sense that it's been solved for a long time. Like I'm talking over 2 millennia ago. We have evidence that Archimedes back in, you know, 200 plus BC was solving the area problem. And it's the solution has been around for a long time. So the idea is simple, and you guys may have even seen this in geometry class or some math class before. If you don't know the area of some random shape, slice it up into smaller shapes that you do know the area of, and then you just add up those areas. Yeah, I don't know what's wrong with this thing. It just stopped broadcasting. Didn't even touch anything. Okay. Yeah, so you slice it up into smaller shapes and you kind of count the shapes, right? So I know the area of each of these. I can take this blob, slice it up into some smaller rectangles. And then, of course, the idea is the area of the larger shape, we define it to be the sum of the areas of the smaller shapes, right? Now, of course, there are going to be some shapes in here where they're not quite rectangles. Like you look at this guy right here, right? He does have a weird edge looking to him. He's not quite a rectangle, but then you can kind of pretend, well, that's like half a rectangle, you know, and you kind of get an estimate. And getting an estimate is completely fine. We spoke about this before, that a large part of math is just about approximating stuff, and that is good enough, because a lot of times, even if we had the real answer, we couldn't use it. So if I know that, oh, I need pi units of something, there's no way in real life I can actually get pi units of something. No one has ever seen the entire number. So approximations are good. So you just approximate. And then if someone's not happy with the approximation, like you want to nitpick with the taxman, what you can do is you can move to those areas and you can repeat the process. Just slice it up into smaller rectangles and then get a better estimate for what that is. So you can kind of do this. So you can do even smaller rectangles to get a better approximation. So you might think we're done there. Okay, so we know how to find the area of some random blob now to approximate it to within any degree of accuracy we like, really. But you don't forget what I mentioned before. Like if someone were to come and give you another random blob, what would you have to do? The exact same process. It's going to take a lot of time, take a lot of manpower. You don't want to be paying people to go to every plot of land and, you know, like slicing it up into little rectangles and counting 1, 2, 3. You're paying people for that. It's a government job? No. Okay. You want a sophisticated way to do this, right? Some way that you can actually apply the machinery of mathematics towards this problem. Okay. So here's one way we can do it. And I don't know, it seems like the screen is freezing. I don't know what's going on with the iPad today. So here's how we can start to do some math with this. We can put that blob on the XY plane, right? Thanks to Descartes for inventing the XY plane. And we're going to start to apply some math to be able to do this. So we know the idea. We're going to take our shape. We're going to dissect it, right? And we want to be able to use what we know about mathematics, like XY plane, like putting it on the XY plane to get to an answer. But you realize dissecting it like that into little rectangles can get a little bit complicated, because what that means now is now you're going to have to keep track of what X's you're looking at and what Y levels you're looking at, which is kind of too complicated. So what we can do is just decide we're going to dissect it in one direction only. So we're looking at, instead of just these small rectangles, we're looking at large strips of rectangles. And we're going to use the area of these rectangles to approximate the area of the curve. The same idea can happen. We can use more rectangles if we want a better approximation. Okay, so now that we have done that, we can put this on the x-axis in the xy plane. And okay, we're going to slice like that. So now let's use our machinery about functions and blah, blah, blah. And we can just create a function that does this curve. Problem is, the blah is not a function. So because it doesn't pass the vertical line test. So what we can do for that is to just, you know what, let's do 1/2 at a time. Let's forget the bottom and only worry about the top. And then we can put the bottom back and do that, right? And find a sophisticated way to do that. So now, all right, yay, this is a function. So what we have now is we have the idea of how we're going to proceed. So now what we do is we create these smaller rectangles inside, just as we did before, but only cutting in one direction. And you can use the area of the rectangles to approximate the area under the curve. And what you can do there is just making sure that the curve can be described by some function that you can create. Right? And so it turns out if we can solve this problem, we can solve the area problem, right? If we can do this in a sophisticated way. And that is awesome. So that's kind of what we want to do with mathematics, is you go from this real world problem that's sort of vague and you want to boil it down to some very basic mathematical idea. In the same way that we looked at the rate problem, we're like, we want to figure out how fast that something is moving, what thing, anything. like what? That's vague. Like, how are we going to do that? But then we just realized that we could boil this down to an idea of what is the slope of this line, right? So answering that question in mathematics just comes down to what is the slope of this tangent line, and so that's why math is useful. Um, I've heard a nice quote. I don't know who first said it, but I've heard it a couple times, and it's so true. I know it says, a lot of people think that math is complicated, but that's because they don't realize how complicated real life is. Math is actually the simplification, right? You have these very vague questions, and math can tell you, just do this and you're done, right? It's concrete. You can see it there. You can draw that straight line. You can find that slope, and you answer your question. Same way, we have now just boiled down finding the area of any random blob to finding the area under some function. And we can do that by drawing rectangles and adding up the areas of the rectangles, right? So now you realize that we can actually control our approximation by how many rectangles we do. So here, okay, it might be a good approximation, but obviously you're missing a lot of stuff, like in here and here and here, right? So what you can do, iPad, is get a better approximation by using more rectangles. So here we're using 4 instead of 2. We'd actually miss less stuff. Here we're using like 7 rectangles, even better, we're missing less stuff. So the idea is the more you can use, the more rectangles you use, the better your approximation gets. So now you might have the question, well, how do we find the exact area, like the actual area under the curve? And then of course the math answer would be, no surprise, use an infinite number of rectangles, right? We're in math land now, we're not in real life. We can just have an infinite number of rectangles. So how do we get that to work is going to be the question. So that's what we're going to do. So let's actually start making this precise. And this is going to lead us into the object called the definite integral. So we pretty much know the process by which we want to solve the area problem. Find the area under a curve, and we can solve the area problem. Okay. So let's actually go about making that systematic, because that's what's important. We have to make the mathematics systematic. Okay. So let's say I have a function and I want to find the area under the curve. What I can do is, let's say I wanted to find it between some point A and some point B. And I want the area under this curve, right? Between this point. Right, so I want this area here. Okay, what we can do is we have to choose how to set up our rectangles. You don't just have a free-for-all and anarchy and like everyone set up your rectangles how you want. No, you're going to come up with a systematic way to do it. So you're going to start to call these guys some x values, call this guy x0. You have n rectangles, you'll call this guy xn. And you can dice it up systematically. So you'd have like an x1, an x2, an x3, and so on. And what you want to do, just for some sort of system or definiteness, what we can do is same width for all rectangles. Call it delta x. So it's like a change in x. And so you'd have, all right, the same width. So what in technical terms we say we've just did is we created sub-intervals. So there's one big interval AB, and we've created some mini intervals that add up to that interval. So these are called sub-intervals, and they're really going to be the edges of our rectangles that we're going to be erecting, right? So now, how do we actually go about knowing what the width is going to be? Well, if we want them to be all equal length, what we have to do is however many rectangles we're using, you take the length of the interval AB, and you dice it up into how many rectangles you're using. So let's say you're using n rectangles. You'll take the length of the interval divided by n, and that's the length of each subinterval. But what is the length of the interval? Well, the length of any horizontal length that you put on an x-axis is just going to be the right number minus the left number, right? What is the length between 2 and 5? Well, it's 3. How do you know? Take 5 minus 2, you get 3, right? So that's the idea. So the length of this interval is b minus a. And to get n equal subintervals, each one has to have length b minus a over n. That brings us to the notes here. We can say that our delta x is going to be b minus a over n. And that is always going to be true. That's what we're always going to take our delta x to be, right? B minus a over n. All rectangles have equals width. Okay, cool. All right, now how do we draw the rectangles? You have to be very specific in mathematics, right? You can't say, okay, just throw rectangles up. Like, no, how far up do we go to do these rectangles? So there are many methods, but we're going to talk about three. We're going to talk about something called the left-hand rule, the right-hand rule, and the midpoint rule. But there are many others: your trapezoid's rule, Simpson's rule, all sorts of things. So the left-hand rule and the right-hand rule, not the right-hand rule from physics, it's a different right-hand rule. Basically, they tell you how to erect the rectangles. In the left-hand rule, we use the left side of the rectangle to determine the height. So we would move up on this first subinterval here, where we have, the a and the x1. That's the first subinterval. What we do is we go to the left side and we go up until we hit the function, and then that determines the height of this rectangle, right? Move on to the next subinterval, x1, x2. Left side, go up, hit the function. That determines the height of the rectangle. Left side, hit the function. That determines the height of the rectangle. Left side hits the function. That determines the height of the rectangle, right? So now I can get, in this case, 4 rectangles whose areas are going to add up to an approximation for the area under the curve. Now, you'll notice for this function, in this case, it's not true in general, but in the example that I'm showing you right now, this gives an underestimate, right? For sure, whatever answer you get from these rectangles is going to be smaller than the actual area because you have spaces missing right here. So you have these little pockets of area that you haven't found, right? So you can have that. Moving on to the right-hand rule, it's going to be the same idea. You're going to, you care about between A and B, right? So you're going to dissect that into some subintervals. That's your x0, your x1, your x2, your x3. B is going to be your x4, which is your xn, where n is 4. And now what you do is you use the right side, and that's the right-hand rule. So the right side goes up, hits the function, that determines the height. The right side goes up, hits the function, that determines the height. The right side goes up, hits the function, that determines the height. The right side goes up, hits the function, that determines the height. Right? And now we can approximate the area under this curve by approximating the area of these rectangles. There is something else called the midpoint rule, where again, you start with the same idea. Ugh, come on, iPad. You want to find the area from A to B. Should be clear here, the right-hand rule, this gives an overestimate in this case. Right, because clearly the area under the rectangles are going to be larger than the area under the actual curve. So the midpoint rule came in because sometimes we want to kind of minimize the underestimate that we have, as well as minimize the overestimate that we have. We want to get to the answer quicker and closer to the answer. So they invented the midpoint rule. And how the midpoint rule is, well, it starts out pretty much the same, but then we kind of switch it up a little bit. So you have these 4 subintervals. And so, yeah, we have these intervals now. But now what we do is instead of taking the left or the right, we take the middle. We take the midpoint, right? So here we have x1, x2, x3. But instead, we're going to choose some other points in the middle. We're going to choose the midpoints between these intervals. And we're going to call that one x1 star and x2 star and x3 star and x4 star, right? And we're going to actually use these middle points to determine the height. And now what you're going to realize is that if you look at this one, if this is the height, what you're going to notice is that on one side, it gives an underestimate, while on the other side, it gives an overestimate. So it tries to balance itself out, right? At least with this function. Not all functions would behave like that. But you can kind of see the idea why someone would want to choose a middle. They kind of get an underestimate and an overestimate at the same time with the hope that this is going to kind of balance each other out and we can get closer to the answer with less rectangles. So similarly, that's going to be the height of this one. This is going to be the height of this one. And this is going to be the height of this one. And then, of course, same idea. We add up the areas of these rectangles to get an approximation for the area. Now, of course, we know the width of each rectangle is delta x. What is the height of each rectangle? Well, it's determined by the function, isn't it? So you'll notice here that we would have the height of this rectangle would be f of x0. This one would be f of x1. This one would be f of x2. This would be f of x3, right? That would be the height of all the rectangles. So we have the heights of 4 rectangles. This one, the heights would be determined by f of x1, right? So the last one, we had f of x0 because it starts from the left, but on the right, it would start from f of x1. The height of the second one is f of x2. The height of the third one is f of x3. And the height of the fourth one is f of x4, right? So here I use from 1 to 4, here I use from 0 to 3, and that's because on this one, I want to keep all the lefts and ignore all the rights. On this one, I want to keep all the rights, ignore all the lefts. Pretty sure that you're not going to be able to see that when it's f of x4. And of course, here we have the midpoints. We have f of x1 star, right, up to f of x4 star, right? You kind of get the idea. Okay, so now let's just look at one of them, how we would actually get to the formula that I have below. Let's look at this one. Okay. Now, what it would mean is that the area of my under that curve is going to be approximated by the length times width of all these rectangles. So I can have here f of x0 delta x, right? That's the first rectangle, that's the area length times width, plus f of x1 delta x, plus, of course, dot, 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 f of x3. I don't know, I should probably just put it in, can do dot, dot, dot for one guy. Let's not be lazy. F of x2 delta x plus f of x3 delta x. This, by the way, there's a shorthand for this with something called the summation sign, a sigma. So it says you're adding up things of this pattern, f of xi times delta x, where the I can be 0, 1, 2, or 3. So you would say your I goes from 0 up to 3. And you just say, I'm adding up a bunch of these things that look like that, right? And this guy is called the left-hand approximation. For the area under the curve. Okay. There's another way, of course, you can think about this, is that your delta x is actually a common term. You could have factored that out. And then you'd have your f of x0 plus your f of x1 plus your f of x2 plus your f of x3, which later is how we're going to be writing it out. So I just want you to know where that expression is coming from. So by looking at the above three methods, the left-hand rule, the right-hand rule, and the midpoint rule, we can develop formulas in the same way I just developed that formula for you. And we can get these guys right here. So notice that the left hand goes from 0 up to 1 less than the highest number. That's because it only takes the left sides. Right hand goes from 1 up to the highest number, n, because it only takes the right sides. The midpoint goes from 1 to n, but with these new x values that we've created in the middle. And you can find those new x values by just taking the average of the two endpoints. Really, you only have to take the average of the first two and then add the delta x to get all the other ones. And of course, your delta x is always b minus a over n. Right? So those are the general formulas, which you don't need to know them in sigma notation. You just need to know the idea, right? But those are the formulas. And so just need to know the idea here, and the idea is the same idea. Where did all that other stuff go? Oh, I didn't write anything else. Okay, so those formulas are important, but really they're kind of just encapsulating this idea. So if you understand that idea without the sigmas, that's fine. Okay, so yeah, now we kind of know that, but the idea still remains about how to actually find the exact area. But before that, let's just see what these are called, because if I ask for them, you need to know. The formulas here are called Riemann sums because they're summations. And they're named after Bernard Riemann, who formulated this way of finding integrals. So like I said, integration has been around for millennia, but the way that we do it in modern calculus 1 class is the way that Riemann did it 100 years ago. So this was how Riemann did it, developed integration in his PhD thesis in like 1905 or something like that. And so that's the method that we use. So it's called Riemann sums, named after a German mathematician. Okay, so now these are finite Riemann sums, of course, because it's just we're using n rectangles. But what about the infinite number of rectangles idea? Well, in mathematics, that's not a problem. That's literally just letting n go to infinity. That's actually just a limit, right? So limits are important, right? So now you can get the joke about what I said earlier about calculus is about the study of limits, really. That's like one word. Everyone thinks derivatives and integrals, but we can't get any of these guys to work without limits. So the exact area under the function is just the limit of these Riemann sums. Let the number of rectangles go off to infinity, and you'll fill in all the little crevices. You'll minimize any underestimate or overestimate. And yeah, that leads us to a different notation because this is now important to us. So in the same way that we figured out the rate of change can be done by finding the limit as h approaches 0 of f of x plus h minus f of x all over h. And we're like, that limit is super important. Let's just give it a shorthand name. And we called it, okay, f prime. In the same way, we call this idea by a shorthand. And it's this guy here. So you have this elongated S. It's actually an S for sum. kind of like how the d and dy dx is for delta, whereas you had, yeah, okay, never mind. So that is what we call this limit, the infinite limit, the limit at infinity of a Riemann sum is described by this notation, and we call it the definite integral of the function f of x. That's the name that we give it. The definite integral on AB. You'll notice that AB are over here. Now, some remarks on this notation. In this notation, the big S thing is called an integral sign. The B is called the upper limit. The A is the lower limit. The F is the integrand. The dx is what we call the differential. And this is a definite integral. And its purpose is to find the area under some curve, f of x. Under is in quotation, because if the function dips below the x-axis, it can kind of makes things a little weird. But I'll talk about that in a later time. Now, how do we compute this thing that we want? We're going to look at the finite Riemann sum cases, right? So I'm going to do some examples for you of how we do this in the finite case. Okay. So let's this be an example, which is definitely an example. It is a question that I would ask you. So consider this function, f of x equals x squared plus 1. Consider it on the interval 1 to 5. Approximate the area under this function using 4 subintervals. There are other ways that I could have phrased this. I could say, or using 4 rectangles, or I could say using n equals 4, right? Because of how we set up our notation, n is the number of rectangles. So I can phrase this in several different ways, but the important thing is using a certain number of blah just means the number of rectangles or the number of subintervals you want, okay? So yeah, so this is a pretty standard question for a finite Riemann sum. So the point here is to just get an estimate, an approximation of what the answer should look like. So let me actually show you how to do that. This is a process you will have to know how to do, which in your quiz on Sunday, I think this will be in the bonus section because the quiz on Sunday goes up to optimization. Let's do it by the left endpoints. We're going to do all of them. I won't ask you to do all of them in one question usually, maybe 1 or 2, maybe just 1, in fact. I'll probably just ask you to do 1 of them. But I'm going to show you how to do all 3 of them so you know the difference. So we're going to do the left-hand endpoints, right-hand endpoints, and the midpoints, right? We're going to use the left-hand rule, the right-hand rule, and the midpoint rule. So how do we actually go about doing this process? So as with everything, there are steps. At least that's how I want you to think about it. I don't want you to just kind of meander around and kind of try to figure out, well, what am I supposed to do again? There are steps to everything. Yeah. Which again goes back to my point. I know it's kind of a weird point to make. It's weird when you're arguing for something that almost everyone believes the opposite. So it's like there's no step-by-step guide for life, but in math there's a step-by-step guide for everything. And people are like, math is hard. No, dude, life is hard. Like you don't know what to do. No one really has anything figured out, and we've been on this planet for like hundreds of thousands of years. Yeah, but in math, like in a few hundred years, in 100 years, we can figure out so much. Okay, left-hand endpoints. I kind of want you to think of this as a 3-step process. I could break it into 4, but let's go with 3. The first thing you want to do when you want to find the finite approximation is 1, you want to find your delta x, right? That's the first thing I want you to do. Now, when it comes to finding delta x, remember there's a formula for it, the b minus a over n. So you just have to remember the a is the left-hand endpoint. So here, your AB is the 1 to 5, right? So A is the left endpoint, and B is the right endpoint, right? That's always going to be the case. So whenever we see A and B in the formulas that I gave you above, A is always the left endpoint, B is always the right endpoint, okay? So we know that the 1 to 5 are the B, and we know that our n equals 4 because they said 4 subintervals or 4 rectangles or n equals 4 right out the bat. So this would tell you how you can find your delta x, right? So here we know that delta x delta x equals b minus a over n. This is going to be 5 minus 1 over 4. That's going to be 1. So that's our delta x, right? And that's step 1. Figure out the delta x, right? What is the width of all the rectangles? Now, the second thing I would say you want to do is to draw an interval and set up the subintervals. Put in all the numbers. Okay. Now that's a mouthful. I'm going to write these shorter eventually, but I just want you to know the idea. So what we have here is we know we're looking at an interval that goes from 1 to 5. I know I want to dissect it into 4 sections because that's what I was told. And the length of each of these sections is delta x, right? Which means if I know the leftmost endpoint, all I have to do is add delta x to get to the second one, and then add delta x to get to the third one, then add delta x to get to the fourth one, then add delta x to get to the fifth one, right? I keep adding delta x. Delta x in this case is 1, so I'm just going to be adding 1 all the time. So you add 1 plus 1, that's 2, still even in calculus. 2 plus 1 is 3, 3 plus 1 is 4. Okay, so now you have all the numbers. Now you just have to pick the numbers that you want, right? So this is what I mean, set up the subintervals. You're going to pick the numbers that you want according to the rule that you're using. So here we want left-hand endpoints, which means on each subinterval, I'm going to pick the number on the left. So on the first subinterval, pick the number on the left. On the second subinterval, pick the number on the left. Third, pick the number on the left. Fourth, pick the number on the left. I would not pick 5 because 5 is on the right, right? But 1 is on the left of the first subinterval, 2 is on the left of the second, 3 is on the left of the third, 4 is on the left of the fourth, right? So numbers are chosen according to the left-hand rule. Take the number on the left of each subinterval. Okay. Right, so now we have the numbers, we have the x values that we want. Now remember what we do is we plug these x values into the f of x to find the height. So here, we're going to step 3. Is we're going to set up and evaluate the Riemann sum. Here's where we're going to throw the height into the mix, right? So we know that our area is going to be approximated by the left-hand approximation with 4 subintervals. And that is going to be, well, we know what that's going to look like. It's delta x times f evaluated at all these numbers. So it's going to be f of 1 plus f of 2 plus f of 3 plus f of 4. Okay, and that's following the formulas I had above here, right? I'm using this format here, right? Notice that it starts at x0, goes all the way up to xn minus 1, which is 4 in this case. So that's what we have. And now we're just gonna plug in the numbers, right? So, and let me just make sure that you realize what this is. Left-hand Riemann sum with 4 subintervals, aka left-hand approximation of the area using 4 subintervals. Okay, and what is that? Well, our delta x we know is 1. And now what is f of 1? Well, the function is given, it's x squared plus 1. Right? So this is going to be, well, 1 squared plus 1. Then we're going to add that to 2 squared plus 1. Then we're going to add that to 3 squared plus 1. Then we're going to add that to 4 squared plus 1. Right? So we're adding all our functions here evaluated. So this is f of 1, f of 2, f of 3, f of 4. Right? And now you add them up. So that would leave you with, well, 1 is on the outside, but then that's 2 plus 5 plus 10 plus 17. And that is 34. 34 square units is our approximation according to the left. Okay. Now we can do the same thing on the right. Right? So that was the left. So, and that's the process. It's going to be very similar for all of them, except step 2 is going to be different depending on the method, the actual x values you pick to plug in. So we have this function on an interval, approximate the area using 4 subintervals and left-hand endpoints, or I could have said using 4 subintervals and right-hand endpoints. So let's do, what would it look like if you did the right-hand endpoints? Let's go through it. So again, 1, find delta x. Yeah. Here again, delta x equals b minus a over n. This is going to be 5 minus 1 over 4. This is going to be 1. Cool. Then you're going to go up to setup interval. Right? And at that point, you're going to be like, okay, I know I'm between 1 and 5. I want 4 subintervals. I'm just going to start adding our delta x to each of these. So that would give me, oh, this would be 2, 3, and 4. Cool. What am I doing? Right-hand endpoints. What do we want? The right hand. Okay, so you pick 2, 3, 4, and 5. Those would be the relevant numbers for the right hand. Then you are going to set up Riemann sum. So here now you're approximating the area using the right-hand approximation with 4 rectangles. That's going to be delta x times f of 2, 3, 4, and 5. So f of 2, f of 3, f of 4, f of 5. So that's going to be 1. This is going to be 2 squared plus 1 plus 3 squared plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1. And just we're plugging in the function into each of these. We're plugging in the points into the original given function. Here, this is going to be, of course, 2 squared plus 1 is 5, then 10, then 17, then 26. It's going to be 58. Notice that the right-hand approximation is larger than the left-hand approximation. Kind of makes you feel like the right hand is giving you an overestimate while the left hand is giving you an underestimate, which in this case it actually is, but we haven't seen that yet. Midpoints, same idea, right? It's the same process. Let's go through it again. 1, find delta x. And I'm pretending I'm starting from the beginning. So I know we found delta x, but I want to do each problem completely. Okay, so find delta x. We have delta x equals b minus a over n. This you would get from the problem. It's 5 minus 1 over 4. It's 1. Okay, cool. Now we're going to set up on iPad. Going to set up into interval. Now, this one is going to be different from the others in the sense that how we set up the intervals originally don't really work. So what again, we begin that way though. We add the delta x and we add it, we add it, we add it. Right, so we first have to figure out these numbers. But now I want the midpoint, right? So now I actually care about the guys in exactly the middle. Now it's obvious what those guys are going to be in this case, but for the non-obvious case, what you would do is you would find the average, right? So you'd find the average between 1 and 2, 1 plus 2 over 2, that's 3 over 2, that's 1.5. And that is the number that we have here, 1.5. Right? Now, once you have that 1.5, you can do the same thing. You don't have to find a bunch of averages. You can start adding the delta x to that to get the next one. Plus delta x. Plus delta x. Plus delta x. So delta x is 1. So you take 1.5, you add 1. What do you get? 2.5. Add 1, 3.5. Add 1, 4.5. These are the numbers that we want. Okay. So that is how we do the midpoints. Of course, 3. Now you set up Riemann sum. Of course, you're going to eval. So now our area, approximated by the midpoint rule with 4 subintervals, well, that's going to be delta x times f of 1.5, f of 2.5, f of 3.5, f of 4.5. And so, of course, that is going to be 1 times 1.5 squared plus 1, 2.5 squared plus 1, 3.5 squared plus 1. Now, personally, I would prefer to write these as fractions. It'll be easier to do, I think. So you have 3 over 2 squared. You know that's 9 over 4. Then you'd have 5 over 2 squared, which is 25 over 4, and so on. And you'll be able to add them up easier. By hand, it is nicer to use fractions, you'll actually be able to add them up by hand easier. And then finally, 4.5. Turns out this would be 45. I'm doing like that whole cooking show thing where it's like, oh, you just mix all this stuff and put it in the oven. Ding, this is what it comes out as. Yeah. To hide the magic. Okay, yeah, that's 45. Now, what is, just to kind of give you an idea of what's actually going on here. Let me paste that in. So here's a picture that's describing what happened. So we had our function, which was x squared plus 1. And then we actually had, we did the left-hand rule, which is represented by the green rectangles here. You'll notice that they're all underneath the curve. So they gave us an underestimate of 34, I think. Then you have the right-hand rule, which are the red rectangles. Notice that the red rectangles are above the curve. So they gave an overestimate. They get 53, 54, 58, 58. But then the midpoint, the white rectangles, you'll notice that they give you both an underestimate and an overestimate. They gave us a much more moderate, mellow, to the center 45, in between what the left and right hand gave us. So that's basically it. That's the process. So that's how we solve the area problem. And this is how we approximate the solution to the area problem with a finite number of rectangles. Of course, I'm going to have to teach you how to actually find this limit. I'm not going to ever show you how to find it directly. I would in the other Calc 1 class, but not in this one. And so I'm just going to show you the shortcut, right? I'm basically going to give you all the rules to begin with and not really go into details about computing that limit. It's going to be very annoying. And yeah, so the rules is to find the delta x, set up the interval with the subintervals, set up and evaluate the Riemann sum. Find delta x, set up the interval, set up, maybe I should also put that here, set up and eval. Find delta x, set up interval, set up and eval Riemann sum. Okay, we always, same process. Okay, that's cool. That's a question, right? And the point of this question is to approximate the area under some curve, and that's a visual. Now, we want to find a nice way to actually do what we just did in the infinite case. And this is going to start with a very weird place. It's kind of one of those foreshadowing things where you kind of realize something in hindsight and then they introduce that at the beginning of the story. So it turns out the nice way to actually evaluate these things in the infinite case will be to first find something called an antiderivative, right? So this is the definition of an antiderivative. It's kind of like you're trying to find the reverse of a derivative, like the antiderivative. Like it's like you want to see a function as what you would have gotten if you took some other function and took its derivative, and now you actually want to find that other function. You actually want to undo the derivative to go to the other function, right? That's kind of antiderivative. So the antiderivative of function f of x is another function, big F of x, where if I take the derivative of big F, I get the little f, right? So if I'm given a little f, I want to know what is a big F that I could use that if I took its derivative, I would get the little f. This is called an antiderivative. I want to know the function I'm looking at. What function did I have to differentiate to get this function? Okay. Now, for x squared, well, you're like, well, I know when I differentiate, I subtract 1 from the power, right? So it makes sense that the antiderivative should have power 3. So that when I do the derivative rule, I would get 1 from the power. I also know that if the 3 became a 2, then what would have to happen is that that 3 would have to come down in front and multiply, which means to get back to the original function, I should assume that this thing that I have was multiplied by a 3. Therefore, I should actually divide by a 3 to find the original. And so what you'll really think here, so to find the antiderivative of x squared, in other words, what is an f of x so that f prime of x would give me x squared. And you can think about it. You'll notice that f of x equals, by what I just said, a third x cubed is something that would work. This guy is an antiderivative. It's an antiderivative since, well, you can kind of see if I were to take the derivative of 1/3 x cubed, the answer would be 1/3 times 3, x to the 3 minus 1, and that would just give me x squared. All right. Okay, so that's an antiderivative. However, there's a question that might seem silly at this point, but should ask. Can we find another antiderivative? Is there any other function that you think, if I took its derivative, I would get x squared? And it turns out there are a bunch of functions. In fact, there's an infinite number of functions that can do this, which is why I said an antiderivative. Why did he say an antiderivative and not the antiderivative, right? It's kind of what I have said. Math is very detailed oriented. The language matters, okay? So the fact that you're reading a math book and it says an blah, 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 as opposed to the blah, 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 right? The prepositions matter, right? It might not matter as much in everyday language when you're talking to your friends or whatever, but in math, it matters, okay? And is used on purpose because there are a bunch. For example, f of x equals a third x cubed plus 5 is also an antiderivative. And once I wrote that down, it should be derivative. It should be clear why that is, because, well, if I were to take the derivative of a third x cubed plus 5, what's going to happen? Well, here I'm going to get an x squared as the answer, and then I'm going to get a 0. I'm going to get x squared again, right? So, in fact, so is, well, a third x cubed plus 7, or a third x cubed plus pi, or in fact, you can realize that this can happen with me just adding any constant. So it kind of goes down to a third x cubed plus c, where c is a constant. It's called an arbitrary constant. because you don't really know what it is unless you're given more information. But at the same time, you know that potentially there could have been a constant there. There might not have been. The original function might have been a third x cubed plus 0, but it could have also been a third x cubed plus 5, a third x cubed plus 7, a third x cubed plus pi, whatever. So we kind of have this constant, this big C as a placeholder for potentially there was a constant here, but that would have gotten wiped out by the derivative, so we don't really know. So what we're doing, we just have a placeholder. This guy here, therefore, this is called the general antiderivative. Okay, because it's the most general form of the antiderivative. And in this case, big F is called the primitive. Okay, so that's just the primitive thing you started off with, and then you just add a C, and now it's generalized. It's also possible for your big F to be different. For x squared, your primitive is pretty much always going to be a third x cubed, but there are functions where the primitive itself can change, but that's like when you have like trig functions and blah, blah, blah. Get more complicated. So that leads us to this thing. Suppose big F is an antiderivative of f of x with no constant term, then this is called the general antiderivative, big F of x plus c. And so here, the c is called the arbitrary constant of integration, and big F is called the primitive of f of x. Okay, cool. So for example, the general antiderivative of this guy is a third, I don't know why that looks so spacey. Fix it later. So this guy, the antiderivative is a third x cubed plus c, where the plus c makes it general. AKA, another way to say this is that it makes it indefinite. Why would we say indefinite? Because we don't really know what the plus c is. So yeah, it's kind of indefinite. I'm not definitely sure what this is. I just know there might be a constant there. And we also have a very important notation for this. So the general antiderivative of function f of x is denoted. And here's the foreshadowing. That's the notation that we give it. We don't give it big F of x plus c. We would call it that. You'll notice that there's no a and b on this. And of course, that's correct because no one even mentioned any interval. We don't know where the interval is. We also don't know what the arbitrary constant could be, right? So this guy is called the indefinite integral of f of x, as opposed to what we defined earlier, the definite integral, right? It's definite. I'll know for sure what the answer is here. But here we have what's called the indefinite integral, right? Yeah. So ultimately, the indefinite integral would look like this. We can say sometimes you leave out the word indefinite, right? So if someone says integral, chances are they're talking about the indefinite one. They would emphasize the definite integral if they're really thinking about an interval. So in general, this would be how you would write something down. So for example, I would say the integral of x squared is x cubed over 3 plus c. So I can say the antiderivative of x squared is x cubed over 3 plus c, or I can say the integral of x squared is x cubed over 3 plus c. These are all synonyms, right? So in terms of notation, the dx is called the differential. It should always be written to the top and to the right. So you can write this, it's okay. You can write this, totally fine. That, wrong. No, the dx cannot be on the left. Okay, it has to be on the outside. Also, boom, wrong. The dx cannot be underneath. Right? Like, what are you doing? What are you talking about? You're putting the cart before the horse. Okay, so that's an idea of notation, right? And by going backwards in how I said, we can come up with some formulas for some general cases. So just like how we had the power rule and blah, 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 we also have some rules for indefinite integrals. You should just memorize them, right? And we can talk about them a little bit more next time. But the indefinite integral of x to the n is x to the n plus 1 divided by n plus 1 plus c. And that's because we're trying to reverse the derivative, right, to get it. The indefinite integral of 1 over x is ln of absolute value of x. Now, the absolute value is important. Don't leave it off. Students often leave it off. Don't leave it off. And that's because whether your x is positive or negative, this will actually work. So you need the absolute values. So you just realized by the chain rule that would work. I actually found the derivative for you before. So you can realize that you can get that. The derivative of ln x is 1 over x, but that x has to be positive. It only gives you the right side. To make sure you can also get the left side of 1 over x, you need the absolute values. You can generalize the exponential rule if you have a constant times a variable with that. And yeah, so just one quick example. Like, for example, if I said the integral of e to the 5x dx, this is just 1 over 5 e to the 5x plus c. Or if I said the integral of e to the minus 7x dx, this is just minus 1 over 7 e to the minus 7x plus c. If I said the integral of e to the minus pi x dx, this is going to be 1 over minus pi e to the minus pi x plus c, right? So the exponential, they're still pretty easy. Okay, so next time what we'll do, which we probably won't be in person doing this, is I'm actually going to compute a bunch of integrals for you to show you how it would be done. And we're really just following these rules that I mentioned in this block. And remember, don't forget your training, Grasshopper. To apply a rule, the thing you're doing has to look like the rule. Don't start applying stuff if it doesn't look like. You have to mold the thing with algebra potentially to get it to look like one of these rules before applying it. So for example, this guy here doesn't look like a rule. It has a radical. Well, how can I make it look like a rule? Write it as x to the half power. Then it would look like this rule, the rule number 1. What about this one? Doesn't look like anything. What can I do? Divide x into each part. Then you'd have it looks like rule number 1 and rule number 2. Right? And so on. Right? And we can get a little bit more complicated, a little bit more complicated, a little bit more complicated, right? But we can just keep going and do these computations. So you can and should try your hand at that. I'll probably put some bonus problems on actually doing these. But it just comes down to following these rules. But we'll stop there for now. Eventually, I'm going to connect this to how we can find the definite integral or the area under a curve using integration with a nice sophisticated formula. And yeah, for now though, that's where we are. So the notes, as I mentioned, they'll be put in ahead of time. So some other things I'm going to talk about is going to be here, the fundamental theorem of calculus. We spoke about that guy. And then we're going to do some of that and do some interpretations. And that's the main thing. We're also going to do another technique called substitution, which is helping us to find, it's kind of like the integral version of the chain rule. And it's going to help us find even more complicated integrals. And time permitting, I'll talk about area under curves. Okay, that's that. Thank you for your time and attention. Enjoy your weekend. Quiz on Sunday, practice tests are up online. You should do them. That will prepare you for the quiz and the test that's coming up the day after. And yeah, it's been great having you guys. This is probably the last time I'm seeing you guys in person other than office hours. So yeah, ta-ta for, I will see you in the next one, just not in person. So that's kind of, yeah. All right, so enjoy your weekend. Have any questions, email me. I will put up your grades for quiz 4 in Jupyter and have you see them. I'm gonna work on that right now. So till then, I will see you guys in the next one. Ciao.